So our subject is benzene, and I want to draw the structure of benzene. So this is benzene. It's a hexagonal. And to understand the pi bonding or the stability of the molecule, firstly we need to we have to determine the point group of the molecule. So we have a symmetry tree here. So we will ask the questions. Linear system, the answer is definitely not. This is not a linear system. And it is not TD or octahedral symmetry. So the answer is automatically no. Do we have a CN axis? So we have a CN here. Actually we have C6, right? Since if you turn it 60 degrees, then the same molecule will be obtained, which is the highest principal rotation for us. So we have a C6. So the answer is yes. Is there an orthogonal C2 to CN? So for instance we have this one. We have a C2, or if you turn the molecule from here to here, you will obtain the same molecule. We have another two, so these are the C2, and we can also other C2s. For instance, we have this one, we have this one, and we have this one. So there are 6 C2 perpendicular to C6. So the answer is yes. For this one, do we have a sigma h plane? So what is sigma h? So we have a CN axis. This is our CN axis or C6, and this is the sigma h plane. So if we apply the sigma h, we will obtain the same molecule. So the answer is yes. If the answer is yes, the point group of the benzene is D6H. So we know the point group, and we have pz orbitals in each carbon. So we have pz orbitals, and we have also phase. What does it mean, phase? For instance, this is the plus phase, okay. This is plus phase. And we have also negative phase. And I want to make the negative phase the different color. So in this case, I will color the upper side of the Z orbital, and this is the minus phase. So we have two phase, and I know our point group. So this is our point group table. So we have E element C6. Maybe I should do it. So this is our point group table, and I want to write the elements here. D6 H is the point group.
A few moments later.
Okay, we have these elements, and I will apply all the elements here. Okay, for instance, if we apply E, what does it mean? That we will not do anything for the pz orbitals, and I will look at the non-changing pz orbitals. If it is not changing for each one, I will write 1. If there is a phase change, I will write -1. If the place of the pz orbitals change, for instance, if this thing goes to the here, I will write 0. So position change. Okay, if I apply the E, it means that we didn't make any change, so all the pz orbitals are in the same position, so we didn't change anything, so it is 6. And we have, for instance, we can apply the C6, and I will apply it, which is our principal axis, right? So if you apply it, it will go here, this 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 will go here, and the answer will be 0 since position changed. 6 of them changed, so the answer is 0. And we have C3, again C3 is here, same thing is happening, so the answer is 0. C2 is also here, we have also C2, and therefore it is 0 since this thing, for instance, go to the here. Therefore position change occurs, which means that the answer is 0. And C2 prime, maybe I should clean this part a little bit. So C2 prime passes from here, one of them. I can look to only one of them, so this is C2 prime. And what is happening is that these two are changing with each other, right? But so we have to write 0 for them. But these two positions are same, but phase changes. So there is a phase change for two of them. Therefore, I will write -2. And C2 prime passes from here. Maybe I can use different color, for instance yellow. Okay, C2 passes from here, so it passes and it cuts the bonds. So this is C2 double prime. In this case, all the pz orbitals change their positions, so the answer is 0. And I equals to C2 times sigma h. So we will apply the C2 here, then I will take the sigma h, and the answer will be definitely 0. Okay. And S3 is similar. S3 means C3 times sigma h. I will apply C3 here. I will take the sigma h, all the positions will change again. So the answer is again 0. S6 again is very similar. C6 times sigma h. And similarly all the positions will change. And sigma h means that all the phases will change, right? Since, for instance, if we apply the sigma h, which is the plane that contains all the molecule on a plane, so all the phases will change, so there is only phase change. And sigma d, so sigma d again passes from here. Okay, you may think a mirror, there is a mirror here. Okay, and this pz orbital will go here, this pz orbital will go here, and this pz orbital will go here. In this case, if we apply the sigma d, it will be 0. And sigma v, so sigma v here will contain, I will draw with yellow, will contain one of the pz orbital. Okay, so these two pz orbitals, these yellow ones, okay, will be in the same position if we apply, but other two, these ones, will change with each other. Therefore, we have two unchanged positions, so the answer is 2. So this is our reducible representation for the pz orbitals. And here I have the point group table for the D6. And we have to find the correct reducible representation. Or I can write maybe RPZ. Okay. And I will give you the answer very fastly. The answer is that A2U plus E2U plus B2G plus E1G. So if you sum these up in the table, A2U, E2U, B2G, and E1G. So if you sum these things, you will find our reducible representation. So this is our reducible representation for PZ orbitals. I hope this part is clear, and in the next part things will be harder. Why? Since I want to build the molecular orbital diagram for the PZ. So you may see that for cyclic groups we draw it like this. So one corner looks to bottom and the other are in the edge, and we have another corner. So simply we can write the energy of the p orbitals, something like that. So we have no node here. We have one node, we have two nodes, and we have three nodes. So firstly, definitely the total symmetric one is A2U. So we have no nodes. And the other one has so many nodes, and it is B2G symmetry. So writing these two is very easy, right? Since I will draw the molecule, I will put the PZ orbitals here. There is no node, so that I will just make, for instance, a positive PZ orbital, so that there will be no phase or no node. There is no node here, and this is our one of the molecular orbital. So this is the A2U. However, if you want to make one node and two nodes, it is harder, and there is no easy way if you don't memorize it. And I know the answer, but right now I will make the question unlike I am not knowing the correct answer. And we can look at the highest unoccupied molecular orbital. So we need to make three nodes. To make the three nodes, I don't have any choice. The phase will shift in each orbital, and I will create the three nodes. For instance, we have a node here, we have a node here, and we have a node here. So there are three nodes. But what about these four orbitals? So these ones are E2U and E1G, symmetry group. And in order to understand their structure, we can use C6 point group table. By using the C6 point group table, I will create the wave function. So this is C6 point group table. So here A represents our A to you. As you see, it is total symmetric. If it is total symmetric, you will see the wave function. I will write the wave function for that. This is not symmetric one and refers to B2G. And this is refers to E1G. And this E2 refers to E2U. And you realize there's an epsilon here. And I will show how to get rid of from the epsilon. So firstly, C6 have E, C6, 6, C3, C2, C3 double, and C6, 5. So all the elements will be applied here. Okay. For instance, if we apply, and we can name them maybe. So this is one of the piezo orbital. I will name it phi 1. So this is phi 2. This will be phi 3. This will be phi 4. This will be phi 5. And this will be phi 6. So we have 6 of them. So if we apply the, for instance, A, I will simply make theta phi 1, phi 2, phi 3, phi 4, phi 5, and phi 6. So I will choose one of the direction, for instance, clockwise. Okay. If I apply phi 6, for instance, which one? So I will turn it, okay. 6 means I will turn it 30 degree. Then this thing will come here. So I wrote the phi 2 and I will go on. It will be phi 3, phi 4, phi 6, phi 5 and phi 6. So this is our first piezo representation after applying the A. And I can write it, my wave function, which is theta 1 plus theta 2, phi 2, phi 3, phi 4, phi 5, and phi 6. And I can normalize it. The normalization is very easy, you know, from the quantum chemistry. Just 1 over square root of 6 plus others. So this is my wave function, first wave function, and it represents this one. So it can be represented like this, and I can apply the B, for instance. So I will take this part and I will copy it. So this is our first wave function. I will write the other easy one, which is B. So if I apply the B here, I will apply it. I will write the answer directly. So it will become, actually B is 1 minus 1, 1 minus 1, 1 minus 1. So it is the asymmetric version. Or we can use the second term. So this term, I can use this term and I will multiply it. And I will make my wave function. I'm just multiplying it. Minus 1 times 4. Plus 1 times phi 3. Phi 3. This is minus phi 2. And this is plus phi 1. And this is my other wave function. I can write it here. And I can normalize it. Again, it will be 1 over square root of 6, phi1 minus phi2 plus phi3 minus phi4 plus phi5 minus phi6. Okay, so this is the second wave function. So, and this orbital, as you see, is here. So this is our second wave function. For instance, I said that this is phi1, right? And minus version of the phi2 is represented here. And this is minus phi2, this is plus phi3, this is minus phi4, this is plus phi5, and this is minus phi6. I guess you understood this. But again, I still didn't solve this part. And how can we do that? So firstly, we know the R. I will clean this part. So we know the E1 and E2. And in E1G, I will have these phi's here. Right. And I will multiply the phi's with these two. And I will make my own wave function. And I will make two wave functions since we have two different numbers. So first I will multiply it with this one, then this one, then this one, then this one, this one, and this one. Okay. And I will write it. This will be our third and fourth wave functions. The first one, which will be phi1 plus epsilon phi2 minus epsilon star times phi3 minus phi4 minus 3 phi5 plus epsilon star phi6. So I will not right now normalize it, and I will write also phi4 or our fourth wave function. So this one wave function 3, and this will be wave function 4. So I will write the wave function. I am just multiplying this one and this one. So phi1 epsilon star phi2 minus epsilon time phi3 minus phi4 minus epsilon star times phi5 and plus epsilon times phi6. So what I will do that, firstly I will add them to eliminate complex numbers. And secondly, I will subtract them. So I will subtract our two wave functions. And I will divide them to I. And it will eliminate coefficients. So firstly, I will add them up, but I have to take them. By the way, this is phi 1. I will just add these two, and I will make a new wave function. Maybe I can name it as this one. Okay, I am just adding so these parts are actually just one. So I could eliminate it actually. And this thing will be equal to just this one. And I can normalize it. So 2 square plus 1 square minus or plus 1 square. I'm just add the coefficients. So for 3 times 4, 12. So square root of 12. So 1 over square root of 12 times my wave function So this is our normalized wave function. So what does it mean? So we have here, so this was phi 1, this was phi 2, this is phi 3, this is phi 4, this is phi 5, and this is phi 6, right? So I will write the phi 1, so this is for instance phi 1, and this is the positive one for instance. Phi 2 is also positive, but it is smaller since the coefficient is 1 here, but it is also positive. Okay. Phi 3 is negative, and its coefficient is 1, and this is 3, and 4 is minus. Okay, 4 is minus, but the coefficient is a little bit bigger, again 2, and it has opposite value with the first one. So I will just color the upper side. So fifth one, phi 5. It is minus. So I will color this part. And I have plus phi 6. Or plus phi 6. So okay. I will just delete these crowded things here. Okay. And I will look at the nodes. So how many nodes do we have? I think we have one node from here to here. So we have one node, and I will copy it. And I will paste it here. So this is our one of the molecular orbitals, and it belongs to here. Okay, it belongs to here. and I can do the others. So in this case, I will subtract phi 3 and 4, these two wave functions, and I will divide to I. Epsilon minus epsilon star over I is equal to 2I sin square 2 pi over 6 over I, and it is equal to square root of 3. Okay, so I will write square root of 3 here. Over I, of course. Yes, over I. So I will cancel this one. Okay. And I will write it. So this is our wave function. And I can normalize it, by the way. I can normalize it. I didn't right now normalize. I just need to make a little space here. So if I normalize 3 plus 3 plus 3 plus 3, 1 over 3 plus 3 plus 3 plus 3 square times this one, this one, this one, and this one. So this is the normalized form, and I will draw it again like here. Okay, as you remember, this one was phi 1, so this is our phi 1. We don't have a phi 1 right now, so this is empty. I will draw the phi 2, which is positive. So this is the positive representation for me right now. And I have positive phi 3. This is the phi 3. 4 is empty. 5 is negative. And 6 is also negative. So we have a node. And this is our representation for other molecular orbital. I will copy it and I will paste it here. I will resize it and I will put it here. Okay. So I will do the same thing for A2U, but I will not make the calculation for this one. So I guess you understood. I will again sum and subtract and divide it to the I. So that one of them will be phi 5 plus phi 6. The other phi 5 minus, not 5, maybe the wave function over I. So if you make the calculation for these two, I will just write the normalized versions. And I can draw their MO. So this was phi 1. So phi 1 is very big for this one. And positive 1, I will just color the bottom. Phi 2 is opposite direction and smaller due to the small coefficient here. Phi 3 is positive. Phi 4 is positive and bigger like the previous one. Phi 5 is negative and phi 6 is positive. So this is other representation for the MO, and I will look at the nodes. So we have nodes from here, and I guess we have nodes from here to here. So we have two nodes as we expect. So this is our other molecular orbital, which is here. Okay. We can name it as other wave function, maybe 5. Okay. And I can make the other one. I guess you understood. So this was phi 1, this is phi 2, this is positive, okay. Phi 3 is negative. Phi 4 is empty, but we have phi 5, and it is positive. So this is positive. And phi 6 here, and it is negative. So we have a node. By the way, this is empty. We have a node from here to here, and we have a node from here to here. So this is the other molecular orbital for the benzene. And I think drawing the bottom one was the easiest one. It is here, and the highest MO is here. So I guess you understood and you learned how to draw a MO diagram for the benzene. How many electrons do we have? So we just have 1, 2, 3 double bonds. It means that we have 6 electrons, and I can put the electrons here. 1, 2, 3, 4, 5, and 6.